Well, welcome to the fifth and final of this week's webinars addressing insights from the MIT Future of Energy Storage study that was recently released. I'm Howard Grimsbeck, your moderator for this session, and I served as executive director of the study. So previous webinars in the series have focused on insights regarding electrochemical, mechanical, thermal, and chemical storage technologies, as well as electricity system modeling that looked at the future role of energy storage in decarbonized electricity systems that rely heavily on generation from wind and solar. Today's webinar focuses on regulatory considerations for high VRE electricity systems. In other words, what are the practical actions to set the rules framework for both wholesale and electricity markets and retail electricity markets that would help real-world electricity systems, including market design and pricing, and again, both the wholesale and retail levels, come close to the efficient use of variable renewable energy generation and storage suggested by the optimization modeling, while also addressing equity considerations. So the study team was very fortunate to have Dick Schmalensee and Paul Joskow, two leading experts on electricity markets and regulation, lead the work in this area. They also had help from a supporting cast. So Dick, he served as dean as the MIT Sloan School of Management from 1998 through 2007. He was a member of the President's Council of Economic Advisors from 1989 through 1991. He was director of the MIT Center for Energy and Environmental Policy Research, consultant for many government and private corporations. Paul Joskow is the Elizabeth and James Killian Professor of Economics at MIT. He was the head of the MIT Economics Department. He was from 1994 to 98. He was also director of the Center for Energy and Environmental Policy Research. And he has many duties also away from MIT, including service as president of the Sloan Foundation and service on university and corporate boards. These are eminent and practical scholars. They've each published over 100 articles in leading journals, more than 10 books. A lot of their research focuses on industrial organization economics and its application to public policy issues, a lot of work on regulatory, energy, and environmental policies. So just a few simple ground rules for this seminar. First, attendees can use the Q&A feature in Zoom to submit questions throughout the webinar, and we're going to leave enough time to address those. And second rule, or not rule, we'll share the recordings and presentations within 2 weeks of the webinar. So with that, I'd like to move forward into the substance of this. So again, this is just the context. There were 3 main messages from the study about what federal R&D policy should focus on in terms of long duration storage. That was addressed in the many sessions that we had on the technologies themselves. Second, the modeling finding that storage can make the regionally tailored net zero electricity systems affordable. And the third one, which is the focus today, we need to reform market designs and regulatory policies to enable equitable and efficient decarbonization. And again, we're focused on that today. So I'm not sure that everybody participated in the seminar yesterday. So this is just one slide on optimization modeling. It shows really efforts to get very close to net zero. So on the left-hand side, we have at the bottom what the systems would look like if there were no limit on carbon emissions. And the top set looks at if you tried to get down to 5 grams per kilowatt hour, which is about a 99% reduction from the 2005 level in both. And the 3 bars represent New England, the Southeast, and Texas, the regions we looked at. And you can see you end up with a lot of wind and solar. You end up with a lot of wind and solar in Texas, even with no limit, but you end up with a lot of wind and solar in the mix. And the system cost of electricity on average, is higher in the 5 gram case very close to zero emissions than in the no limit case, but not that much higher. So the challenges vary across regions discussed yesterday. Energy can substitute or complement all the other elements of a power system discussed yesterday. We'll talk a little bit about transmission today. And I guess with this background, I'd like to move over to, I believe, Dick.
Indeed.
And so let's move forward into the substance of today's session.
Thanks, Howard. So we looked at more than what are the costs and what are the technology mixes. We looked at what do these markets look like. And one feature that popped out immediately as a robust feature is there will be more low prices and more high prices than today. If you look at the graph on the right, it gives you wholesale prices in Texas, in ERCOT, in 2018 and 2019, and most of them are between $5 and $50 a megawatt hour. Then we looked at 2050 under various carbon constraints, no limit, 50 grams per kilowatt hour, and so forth. The first thing you see is if you look at the dark bars, which don't even appear today, they grow. That is to say, the fraction of time when prices are between $0 and $5 rises as the carbon constraint tightens. That might seem odd because, as Howard just points out, the average cost goes up when you tighten the carbon constraint. But storage substitutes, a generation substitutes for storage. So if you have cloudy days and a tight carbon constraint, you can build more storage, but you can also build more solar generation. And it's efficient to use both. So it's efficient to build more variable renewable energy capacity than when the carbon constraint tightens. That means the fraction of time when the zero marginal cost generation is on the market goes up. So you get more very low price, very low wholesale price hours. To balance and to cover the high costs, you get more high price hours. Not as visible here, but we'll see that in a second. The other thing that's going to be a big feature in future systems, and you're beginning to see it now in places like California and Hawaii, because you can do small scale solar generation, you can do small scale storage. If you do it in volume, we just lost the slideshow, Howard.
My goodness.
If you do it at volume, it'll affect the wholesale market. So the notion of having lots of capacity behind the meter, so to speak, that is having a big effect on the wholesale market requires some regulatory change to make it work. Next slide, please, Howard. This is to just look at, well, suppose you have more storage technologies. The previous slide looked only at lithium ion and compared again current prices on the far left with prices under tighter carbon constraints. The base case is lithium ion only. The second is lithium ion plus redox flow, then those two plus thermal storage specified, and then hydrogen under various assumptions. I don't want to talk about all that. I assume it was discussed earlier. The point I want to make here is if you go left to right, you still see those blue bars rise, the dark blue bars, as the carbon constraint tightens. As the carbon constraint tightens, you are going to get more hours of very low wholesale prices. And to balance, not quite as many with long-term storage, but you're going to get more hours of high prices. So that's by way of background. Paul?
Thank you, Dick, and thank you, Howard. Good morning or good afternoon to everyone, as the case may be. As you can see, we have kind of a round robin presentation here to make it more exciting. This slide that you see refers to the work that we did examining a variety of studies of the impacts of expanding transmission capacity in the United States and its effects on the costs of meeting decarbonization commitments and the effects on storage. And the primary stories are that expanding transmission capacity in particular ways to support wind and solar resources, reduces costs, and it also acts as a substitute for storage in local areas. Now, why is that? Well, there are a number of different reasons. First, the best resources, wind and solar resources, are not located at the same places as the best thermal generation resources are. They're in the Midwest, they're offshore. In the case of wind, some areas closer in upstate New York, or they're in the South, especially the Southwest. And load is not located in those areas as necessarily. And as a result, by increasing transmission capacity, we gain better access to the best resources, which are wind and solar resources. Second, expanding transmission capacity allows us to expand market areas and basically to diversify the intermittency of wind and solar generation. And this reduces the cost of achieving a particular reliability level, as well as the costs of generation services. And third, and I think this is implicit in many of these studies, expanding transmission capacity also facilitates expanding market areas. So not only does one diversify supplies of intermittent generation, but one also diversifies demand as well, and increases opportunities to take advantage of demand resources, demand response resources, and to, again, to take advantage of the law of large numbers by aggregating a wider area on the demand side. Unfortunately, we all know that building long-distance transmission lines in the United States is not so easy. In fact, it's pretty difficult. You've read about the problems Massachusetts has had completing a line to Quebec to gain access to hydro resources there. There are similar issues in New York State at the present time. There's a merchant project that starts in Wyoming and anticipates selling wind into California that, if my arithmetic is right, has been under development and construction for 16 years. That's a long time to develop a project. And there are many issues here in terms of financing issues, permitting issues, conflicts between the states, conflicts between local municipalities, conflicts between other uses of land, recreational uses, offshore uses by fishermen and people taking advantage of recreational opportunities. And from my perspective, if we're going to proceed in this way, we need to start resolving some of these problems. And I've given a couple of other webinars to discuss these issues in more detail. Howard, next. Okay, let me now turn to some wholesale market design challenges that we discuss in the report. First of all, I should note that not the entire country is restructured and has wholesale markets, but we discuss both the more traditional utilities as well as restructured utilities that rely on wholesale markets. And let me focus on some of the challenges with wholesale markets. We already have issues with wholesale markets in terms of supporting new generation, supporting not only the operating costs, but the capital costs of new generation. Most of the ISOs in the US have price caps. They also, system operators engage in out-of-market actions often to maintain reliability. All of this affects wholesale market prices. And there is no ISO in the US that does not have, in addition to the wholesale energy markets and wholesale ancillary services markets, some type of capacity remuneration mechanism, some type of supplemental capacity remuneration mechanism to support the total cost of new generation, whether it's the ORDC and ERCOT, or it's the capacity markets in New England and New York, or it's the contractual obligations in California. the money isn't just coming from the energy market. And we anticipate that this problem is going to get worse because, as Dick just articulated, we're moving to a system where we have many more hours of zero prices, and that means they're not providing any economic rents, quasi-rents, to help to support generation, and many more very high-priced hours, which account for a lot of potential revenue, but which are likely to be capped by regulators or to involve actions that don't allow all of the revenues to be realized. To compound this problem, the whole way we think about reliability in systems that are dominated by variable renewable energy, by wind and solar, are just wrong. You're not the peak load in California is not at noon in the summer anymore. It's more like 7 or 8 o'clock at night, and different resources make different contributions to reliability, and this requires a much more sophisticated analysis of the stochastic properties of wind and solar technologies, the stochastic properties of systems with wind and solar technologies. And it's the typical case of saying we're going to have a 15% reserve margin or 20% reserve margin. And it's just hard to design markets that give you the right mix of technologies. And we're already seeing states intervening in these markets, pushing storage capacity, in particular in California, pushing in offshore wind in the Northeast, and so on. So there's going to be a real challenge for how capacity will be paid for, and what these supplemental compensation arrangements for VRE generation should look like. One feature we want to emphasize is that whatever that mechanism, it should not distort incentives of the generators on the margin. It should not give them incentives to keep bidding when prices fall below zero. It should basically allow them to operate in a way that reflects the fact that their marginal costs of operation are close to zero. And you can sign contractual agreements, or you can provide subsidies in ways that distorts that decision, and that can lead to all kinds of distortions, not only in short-term wholesale prices, but also in incentives for generators to enter the market. Next, Howard. Okay, let me talk about some storage-specific wholesale market design issues now. First of all, I think we should all understand that once storage is installed, for it to operate efficiently, it must be fully in the wholesale market. It's got to buy at the spot energy price, whether it's day ahead or real time. That's a choice for generators. And it should be, when it's charging, it should be paid spot energy prices for discharging. And you should expect to see for particular storage technologies, charging and discharging fairly quickly up and down, responding to market conditions. There is then again the problem, well, what if there's not enough revenue in the wholesale market to support the storage? And I can tell you right now, in most places, there's not enough revenue in to do arbitrage to pay for the cost of storage. As a result, there are supplementary capacity payments that are being made, often through state procurement mechanisms or through other orders to distribution utilities, and we need to make sure that these payments are focused on the fixed annual payments per megawatt of capacity and for duration, and does not distort the actual utilization of the facilities. And I think if you look around the world, the UK has probably made the most progress on this in their auctions and how they value different types of capacity. As with variable renewable energy, storage also plays a very large role on the reliability side, because, for example, on the margin, more solar capacity in California may not contribute much to reliability, but if you add storage to it, you think of them as working together, they can add they can add almost full capacity into the market. And we really do need more sophisticated analysis of not only the contribution to reliability of VRE generation, but also of storage and of hybrid systems where storage and generation meet together. It's also important that in my view, the capacity remuneration mechanisms should be determined through some type of competitive procurement system, because storage is going to earn revenues, net revenues from charging and discharging, and we want those expected net revenues to be reflected in any supplemental capacity prices they get for the capacity and the duration of the storage. And the best way to do that, rather than trying to estimate them administratively, which happens in a lot of capacity markets, is to have competitive procurement so that the owners can take into account their expectations of what future energy prices and ancillary service prices and revenues will be. It's also becoming increasingly obvious, both in the US and almost everywhere else on Earth, that long-term contracts are beginning to play a very significant role in the development both of VRE generation and of storage, and I should add, and of transmission capacity. It's important that the long-term contracts be designed properly so they don't distort the efficient incentives to charge and discharge the storage when it's produced, similar to the case of VRE generation. I think relatively little thought has been given to this in the policy arena, because there's been a rush in some areas to push storage into the system. And then there are wires-related benefits. We emphasize that storage complements and substitutes basically all other components of electric power systems. When storage provides wire-related benefits, for example, deferring transmission by reducing congestion, it should be compensated for these benefits. And there's been a lot of talk about, we'll treat storage as only transmission, or we'll treat it only as if it's generation. And that's just wrong. I mean, storage can provide both transmission and generation services from the same facilities. And it's important in making selections that storage be permitted to participate in both of those systems. And in particular, I would emphasize that allowing storage to compete, whether it's through real competition or through the transmission planning process, to compete in a way with more traditional wires development, so that they can take account both of the costs of providing the transmission service, but also the net revenues they'll earn from providing other services. And I think that the discussion about how storage is integrated into transmission planning and development really needs much more attention. And quite frankly, I'm disappointed that FERC is in the process of abandoning the pro-competition aspects of Order 1000, which really would have allowed storage to participate in the selection of transmission capacity in a way that integrated the revenues from both the energy markets and the costs from the energy markets and the residual costs of installing the storage to provide congestion relief and other transmission benefits. And I think I turn it back to Dick now.
Terrific. Thank you, Paul. I hope people understand that we haven't solved these kinds of problems. We think it's important to pose them and to get smart people and people engaged in the real world to think about them. I think retail rate design is at least as hard and at least as important. Economists have said for decades that, gee, wholesale spot prices, marginal cost of electricity, varies over time. Clearly, efficiency calls for rates that people face to vary over time. And everybody yawns when we say that. And in fact, prices don't vary that much per the ERCOT data earlier, except on a few occasions. But the objective here, I think, in thinking about decarbonizing the electric power system is to contribute to economy-wide decarbonization. So, on average, if you're going to cover costs based on retail charges, they're going to have to go up in some sense. But there will be times when the cost is zero. The cost of more energy is zero. And if you want to encourage electrification economy-wide, you want users to see that. The story I tell all the time, and everybody on this call has probably heard it 12 times, is my son in Hawaii loves his electric vehicle, and it costs him 30 cents a kilowatt hour to charge it, even when the Hawaiian system is trying frantically to curtail excess solar generation. That is wrong, and it's going to get more wrong. So, and the other issue here is, to go back to that first slide I discussed, when you recognize that behind the meter photovoltaic and storage is getting to be more important and it will have a bigger impact on wholesale markets, for that impact to be net, effective, and efficient, it's clear that if retail rates don't relate to wholesale market prices, you'll have two uncoordinated sources of supply and demand hitting the wholesale market. Now we can live with that, even with a lot of solar rooftops. But in the future, as we get more penetration, that's going to get worse and worse. So what do we look for in terms of thinking about how to do retail rates? I see three principles here. First, if you're going to get efficient behavior at the retail level, consumers have to see spot energy prices, at least on the margin, particularly when they're low. You want to encourage people to buy electric cars, make it clear that if they're flexible in their charging, it's free. And you also, of course, want to deal with high prices. And that's the second. You can't charge consumers spot wholesale prices for everything. We saw that experiment run in Texas, and every so often, wholesale prices, spot prices, marginal costs explode. And the risks associated with doing that are intolerable. Nobody's going to sign up for another griddy in Texas ever again, even though economists say, no, that's right, it should all be spot prices. So you can't have them pay spot prices for everything. That's just not politically on. The third principle here is that, look, most of the costs are fixed. Storage costs, solar and wind generation costs, transmission costs, yeah, they're variable costs, but they're pretty small, and mostly they're fixed costs. And think about telecommunications, in which most of the costs are fixed. We don't pay any more per call. So ideally, we should recover fixed costs appreciably through fixed charges. But it clearly makes no equity sense to charge every electricity customer the same per month fixed charge. That doesn't make any sense equitably, and hence wouldn't make any sense politically. So if you think through those three principles, the question is, how do you let customers see the marginal energy price, which corresponds to the marginal cost to society to get more energy, and corresponds in a well-functioning wholesale market with the spot wholesale price? But you got to keep the variation in the bill, in the average per kilowatt hour cost, at acceptable levels. Next slide, please. Howard, next, please.
I'm trying. Oh.
I would tap dance if I could tap dance. Okay, so how do you do this? First of all, we could figure out if I could control a monopoly load serving entity, maybe I could design a pricing approach. But frankly, state commissions are an issue here. And state commissions have tended historically, think about their reaction to time of use pricing, let alone real-time pricing, have resisted change. But change really has to occur here if we're going to do economy-wide decarbonization at a tolerable cost. So retail competition might be the answer, although griddy in Texas, which charged the wholesale spot price, is not the answer. So the question of what's the role for retail competition, it might have a more important role now than in the past. The second point here is, at some point, you got to find a way to do fixed costs, fixed charges. uh, it's been suggested by colleagues in California that what the heck, base it on personal income. Forget about electricity. That might happen, that would be interesting, but I think more plausibly, the fixed charge would be a function of consumers' history or rates going forward and the choice of rate schedule. There are two sort of approaches that I don't think either one has been worked out fully, but there's two sort of approaches you can read at the working paper level. The first is hedging. Frank Wolak at Stanford has been an advocate of this, and the basic story here is pretty straightforward. Suppose a customer purchases Q naught in advance as a price P naught, and then pays the spot price, the wholesale price, when you deviate above or below Q naught. You pay more, you pay if you go above, you get paid if you go below. Now, the cost of putting those hedges in place, suppose you did it annually, would be a customer-specific short-run fixed charge. And the incentive and the hedge structure means if the wholesale spot price is really high and the consumer notices it, they have strong incentives to reduce demand, that is to say, to sell to the market when the wholesale price is high. But the problem I have with this is if you think about consumption and spot wholesale prices vary systematically by time of day, day type, season, and so on, this variation will increase. So figuring out what hedge prices and hedge quantities would make any sense and how you would implement it with typical residential consumer makes my head spin. So the question is, can we find a way to use to capture some of the benefit of a hedging structure in ways that are implementable and understandable? I think that's an important question, and I don't have an answer. The other approach, which is in some working papers we've written, says, suppose you imagine an insurance regime. There's just one number. There's a ceiling price P star, and the customer pays a fixed fee, probably based on recent load profiles or whatever. You pay a fixed fee based on P star, and you can buy as much as you want at anything below P star if that's the spot price, but you will never pay above P star even if that's the wholesale price. So you're insured against really high prices. The key advantage of this scheme is you're passing through really low spot prices. So all the zeros get passed through. The disadvantage is, since you never see a price above P star, what's your incentive to reduce your demand when the system is under stress? And it seems to me most logical that nobody will pay attention when the system is under stress, and you need some regime to get adequate response to high spot prices. I think that's likely to be automated load control. If you sign on to this insurance scheme, which you're nuts if you don't in the future, then part of the deal is we do certain kinds of load control under certain circumstances. But I don't know if that can be made adequate. I think we need a lot of work here. And per the last bullet, I think there's much more research. This is not, particularly at the retail level, this is not proving theorems. This is figuring out what will work for consumers, what will be perceived as equitable, and where can we go. But let me just say, this whole decarbonization of the power system is part of economy-wide decarbonization. And if that's the target, what we charge consumers for electricity when is a key instrument in getting efficient economy-wide decarbonization. So this is an important problem and sadly a very hard problem, but there we are. Thank you all very much.
All right. Well, thank you, Dick and Paul. Great tag team presentation. We have questions, a bunch of open questions already. So let's turn to those. I think you could still add questions if you'd like. There's a question, I guess it was for Paul, but it seems to me it would be for both Paul and Dick. What are the market design implications of more distribution level and behind the meter storage? Won't that enable more supply-demand balancing at the distribution level particularly in a transactive system that uses market prices as engineering control signals. So it kind of ties the notion of how behind the meter storage and generation and distribution system storage and generation.
Go ahead, Paul.
Well, in our chapter, we didn't model the distribution system, but in another chapter, there is modeling. I think in terms of behind the meter PV and storage, the primary problem as I see it is the incentives that we have in many of these systems, both for installation and for utilization, are far from ideal. And the result of that is we may get too much or too little installation, and we may get utilization at the wrong times. I think a challenge will be to better integrate through economic incentives or contractual requirements behind the meter PV and storage with what's going on in the wholesale market. We don't. It would be counterproductive if we had incentives for storage to take place at the individual customer level at a time when for the whole system level, where rather than charging or discharging, we're doing it the opposite way. At the distribution level, it's long been known that in the old days it wasn't storage and VRE generation. It was gas turbines. You could use gas turbines to substitute for increases in expansions of distribution systems. And I think it's going to be, in principle, it'll be easier to integrate distribution investments and utilization in grid-based, in distribution-based generation storage in principle, again, if the incentives are there. But we've created this distinction between transmission and distribution, and we've put transmission and anything on the transmission system into the ISO, and it's all subject to FERC regulation. Whereas if it's on the distribution system, roughly less than 69 kV, it's a state regulated entity. And again, trying to integrate the two together is really very important. And I think FERC has certainly issued some guidelines to facilitate that integration. And I think it's now really up to the states to think about how they can participate in making the whole system operate more efficiently and reliably.
Yeah, let me just say, I agree with the questioner's premise that behind the meter storage and generation can in fact contribute to stability and can do a variety of things, but it won't if the incentives are wrong. If you have a lot of PV in California that's getting compensated at a flat retail rate, regardless of what's going on in the system, it is not going to make up necessarily a positive contribution. So as Paul says, yeah, the potential's there, but the key to realizing it is getting the incentives right and enabling the behind the meter systems to respond to those incentives.
I might add one thing. I refer back to a previous study that Dick led on the future of solar. On-grid PV is just cheaper than, it's less expensive than rooftop PV. And nobody wants to recognize this, but it's the reality. Yeah. And so that's one cost we're already paying in incenting expansion in that dimension rather than on the grid. But another cost is if we end up utilizing it wrong, if we don't provide the incentives to put in storage when it should be put in, if we don't put in the incentives to position the rooftop PV in a way that maximizes its output, we're just adding to what is already a cost of regulation.
Yep.
Okay, great. Well, there are a couple of questions dealing with the role of distributed energy aggregation. Could a commercial actor act on behalf of numerous consumers to do complicated hedging? Maybe this would be more acceptable to consumers. And also distributed energy generation aggregation and storage. Is there a role for aggregators to kind of work with consumers to offer these sort of products on a voluntary basis?
Oh, I think
Yeah.
potentially there is. It's a question of what regulators allow and what market designs allow. I mean, there are examples. I'm in Vermont at the moment, and there's a company that sells to the local, an aggregator that sells services of behind the meter storage aggregated to the local utility. And that's a good thing. It's technically feasible. You can link lots of different generation and storage systems. The question is, does that aggregator get the right incentives? Can you do the right contract? But that may be a way to break through some of the conservatism of regulatory agencies, is to work with aggregators. But again, if you're going to pay solar generation a constant per kilowatt hour price, it's going to be hard for aggregators to kind of unwind that. So yeah, aggregators can potentially play an important role. They're, I think, in various parts of this country, and maybe others for all I know, playing growing roles, but it's all a matter of what's permitted.
Yeah, and I think that certainly at the federal level, at FERC, there's considerable sympathy for allowing aggregators to enter into the market. Nothing much happens at FERC quickly, in my experience, so it takes time, and all the interest groups have to have an opportunity to express their views on this. But I think in principle, we're going to have to make use of distribution level and behind the meter capacity and energy to keep the cost down. And again, they need to be integrated into the wholesale market. And we're going to need aggregators to do that. I don't think we can expect small individual customers to be spending their day buying and selling energy in the market. And it's one of these things where it's going to require cooperation between the aggregators, the distribution company,
Right.
The bulk power system operator, and the consumers to come up with guidance for how this can take place in an efficient way and without hurting anybody, without electrocuting people who are fixing the distribution lines, for example. So I think it's an important challenge. I think it's something that there's a lot of thought going into. In New England, if you look at the ISO today, it appears we have almost no solar in New England. And your first blush, you look at the ISO, so of course it's New England. The sun doesn't shine here in the winter after 4:15. Well, it's not that. We have a lot of solar PV on rooftops, on the distribution system, and it's really important to integrate those with the wholesale market so that the incentives to utilize it are clearly aligned in the proper way.
So we say it's important that retail customers see basically the price signals, the marginal costs in the wholesale market. It may well be, and probably is, that the efficient way for them to see it is via aggregators. Yeah. And the aggregators need to have full standing to buy and sell in the wholesale energy market.
Okay, so one questioner asks, talking about the fixed charge, and that more of the costs of the system, the VRE system with storage, are going to be fixed charges, not fixed costs, not variable costs. Asked, shouldn't the fixed charge be based on contracted or metered power? So I guess it's kind of like the system in France, I believe, where you buy a certain maximum power capacity. But what do you think about the role of fixed charges and power? I know we could talk about this for an hour.
We could talk about this for an hour.
Let's not. But let's talk about
it. I'm familiar with the system, and basically in France, if you're a residential or commercial customer, you contract for a maximum capacity on your interconnection with the distribution network, and increasingly more and more costs are going into that, and that allows the energy costs to be designed. And that approach makes a lot of sense to me, and it makes a lot of sense to me both on the fixed charge basis, but also there is a correlation between income and the capacity that is utilized, so that system also has more favorable income distribution attributes. It's not the same thing as charging based on income, but it moves you at least in that direction. So what they call a subscription model, I think is kind of an interesting thing to explore.
I've always liked that as well, but it isn't perfect from an equity point of view. and one of our advisors from Southern California, in response to a sentiment like that, said, well, there are plenty of people who in our area live way away from Los Angeles to minimize residential costs, but of course they have higher air conditioning costs. So you've got poor people living in the desert buying a lot of electricity, and you're just going to whack them with a high charge, and that's going to cause a political backlash. So I think there's a lot of exploration to be done about what's going to be perceived as fair. I mean, if your maximum kilowatt consumption is perceived as the fair charge, then so be it. If not, then what's better? I think at the end of the day, while there are efficiency implications, at the end of the day, this really comes down to what's going to be socially acceptable.
Right. So there are several questions about. It is interesting that there's. It strikes me that there's a lot of concern and national news coverage of situations like have occurred in California, where the bulk power system has to resort to, let's say, very short rotating outages, to deal with an imbalance between supply and demand. And yet, those kind of outages are very similar to the type of distribution outages that occur all the time, that affect millions of people, that, lead to local news, but don't necessarily lead to national news. And I guess my question is kind of, what do you think about, distribution system reliability issues versus bulk power system reliability issues, and why they're treated differently now, and how that can be addressed in a system that has more VRE and storage?
Oh, that's you, Paul.
Well, I mean, just to get the facts straight, I don't have the exact numbers right on my mind, but I would say on the order of 90% of the hours of outages occur because of failures on the distribution system. And these are everything from trees falling down during storms, cars crashing into poles, flooding of substations, as well as occasionally equipment outages. And maybe 9% or 90% of the remaining 10%, 9% are due to transmission system outages, and 1% of the hours are due to shortages of generating capacity and rolling blackouts. And I must say, it's kind of a mystery to me as to why you get all this publicity. For example, in California in August of 2000, early September of 2020, they had 4 hours of outages, rolling blackouts. The whole system wasn't out, they rolled it. Whereas if you look at, for a typical customer, it's trivial. And part of it has to do with the fact that when you have a potential shortage of generating capacity to meet demand, part of the response is you go on the radio and you plead with people to conserve energy, to move the charging of their vehicles to earlier in the day and outside the 4 p.m. to 8 p.m. side slip and so on. Whereas you hear nothing about these local outages that occur all the time. And that's a function of the media, it's a function of education. And I think the irony is that the criteria that are used to establish the reliability requirements for the bulk power system imply a value of lost load that is much higher than is applied to the development of distribution systems. And there's really never been an effort to coordinate these things.
I mean, we're in New England, and you have a major snowstorm, and you could have 100,000 people or more without power for 24 hours, which dwarfs what happened in California. And it's big news locally, but since there aren't deaths and there's very little property damage, it doesn't get any national coverage. It is kind of strange.
Now,
and you can solve all that by undergrounding everything.
Yeah.
I was on the board of a utility, and every shareholders meeting, people would come and complain about reliability, and the response would be, well, we serve a largely suburban area, and we could underground the system at a cost of 7 times the gross national product, or you could live with occasional outages. And those were relatively short meetings.
I mean, ERCOT, what happened in ERCOT in February of 2021 is a different kettle of fish.
Yeah.
And it is extremely atypical. It's a situation in which a large amount of load was shed for roughly 70 hours when it was very cold in a system where there's lots of electric heating. That's really a completely unsatisfactory outcome. But it's also extremely atypical. A question lots of people have, and I think it's good, are we going to see more of these down the road as the climate changes? And if we are, we're going to have to adapt the electric power system to account for that. I think there have been lessons learned from that experience. As all of you've read this over the last few weeks, it's been extremely hot in the West. Every day, people are worried, wringing their hands that they'll have to have load shedding. But so far, the system has held up. And even if they have to have a little bit of load shedding, that is not a terrible outcome, especially if people can be warned and they're not out for too long.
Right. Okay, so here's like maybe a related question leaning more toward Dick. It says consumers can't afford to think through the short-term price decision, so there needs to be automation. To afford automation at the consumer level, there has to be a degree of appliance and car automation. And what is the role of standards, both national and international, in facilitating adoption of the automation? And is the automation, how will it deal with a retail rate system that varies by city, county, state, and country? So the notion is, how do we get products to, I guess, be able to deal with this? And I would say probably also meters themselves, because one option to rolling blackouts may be to dynamically throttle maximum power during periods of system stress. We already have a lot of function in smart meters, but that function of maybe, reducing by 5% the amount of power you could, each consumer could take. So there's a lot of questions about automation, I guess, and how that works in this world of VRE and storage.
I think those are really good questions, and I would love to be able to answer them. I think the core to this approach going forward has to be smart meters with capability of receiving price signals and maybe other signals from some center, distribution or otherwise, because you have to be able to say, if you're going to do automated control, which I think you are, you have to be able to get the signal, now is the hour, to the smart meter. And then the question is, what does the smart meter talk to? How does it talk? What about the car? Does the car talk to the smart meter or something else? My sense, and of course I'm only an economist, my sense is that these are not profoundly hard technical problems. The issue, as the questioner suggests, is going to be standardization, right? Like this little issue that in Europe, every electric car charges with the same plug. In the US, different manufacturers have different plugs. It's like, oh, give me a break. You need standardization there. Maybe you'll get it wrong, but better that than we have a competitive tussle over charging facilities. The same thing is going to happen at retail level. I mean, ideally, there will be minimum standards for smart meters, and there will be various standards for thermostat and other linkages to smart meters. But I mean, people are already building appliances now with the ability to communicate wirelessly. Refrigerators have been out for a while, and others, and air conditioners. So I don't think it's hard. I think it's hard getting standardization and protocols. I may be wrong, and if I'm wrong, I'm going to be sad about it. But I think it's an issue of standardization and protocols, not an issue of developing technology.
Okay, so we're getting close. We have 6 minutes left. I just want to let me put one question out there. It's very parochial, I guess, to Massachusetts. And do either of you have quick thoughts about the Massachusetts Clean Peak standard that was recently implemented? Again, it's related to this, but not, so you don't have to, but
I'm not familiar in enough detail to have a view.
Neither.
Okay, fair enough. And then a question about why are existing utilities not able to provide the hedging and insurance for retail customers, along with the types of rate structures that you want? And the idea is that this is what utilities already do today. So I think there is some utilities I know purchase whatever power in advance, and some on the spot market, maybe some long-term contract. So provide some kind of hedging. So the question is, I don't think that's the type of hedging Dick was talking about, but
No, I mean, large customers can hedge in a variety of ways and find counterparties. Me, no.
We have to recognize, I mean, you can't talk about a generic utility in the United States. Where I'm sitting right now in Massachusetts, the local utility isn't allowed to do any of that. We have retail competition. All they're allowed to do is provide the most basic backup rate for default rate for customers who don't sign up with a retail. And they wouldn't be allowed to offer hedging products because they're not allowed to offer any products. And that's true in most of the retail competition states. In states that have more traditional utilities, or in states where they have not introduced retail competition extensively, like California, and where the utilities are contracting for energy to meet their customer demands, in principle, there's no reason why they couldn't provide these kinds of hedging contracts, or some of the load control options that Dick talked about earlier. And indeed, load control options for hot water heaters, air conditioners have been available for decades. They're very, very popular. And there's no reason why those couldn't be expanded for utilities that still are allowed to do that kind of thing.
If I'm Walmart, I can go to Goldman Sachs and say, the local utilities in my areas can't give me the kind of hedges I'd like to reduce risk. Can you guys find counterparties, and let's see if we can do hedges? You know, if you're big enough and you have access to the right players, you can get contracts written. It does not help small consumers. And if the utility can't do it or won't do it, or the regulator won't let them do it, it isn't going to happen. I also think figuring out what the hedges should look like is not a trivial problem.
Right. Okay. And there's one, I mean, so there's a commenter pointing out that a fixed utility rate that's typical for the present system, is like a hedge, but on the other hand, it isn't a hedge that promotes the efficient running of a system that depends on, VRE and storage. That's really
it reduces risk, but it doesn't incentivize efficient economy-wide decarbonization. Right. And as the price goes up, it'll push against decarbonization economy-wide.
Okay, and there's I guess just 2 minutes left, but there are many questions, but there's one that talks about the idea of splitting the generation product into primary generation, which is the injection of primary energy into the grid, and also secondary generation, I guess, as a ramping and reliability product to mitigate intermittency. Does something like that make sense in your views?
Well, yeah, and most of the ISOs are working on that. I mean, they basically different products,
right?
Fast ramp products, products that can be turned on very, very quickly, and to basically set up separate markets that are, I mean, the markets are separate, but they have to be co-optimized so you don't get all kinds of weird behavior. But I think that's inevitable, because with systems dominated by intermittent generation, you're going to need fast response resources, whether they're storage or their generation resources. And unfortunately, what some systems are finding that they have to do now is they don't have enough fast resources on the system because it's a historical system. So they may start up a coal plant and at 7 o'clock in the morning when they don't really need it until late in the afternoon, because you can't just turn it on and off very easily. So the range of products that the ISOs are developing are very much focused on responding to the needs of responding to intermittency, and that includes fast response resources.
I just point out that if you use coal plants in the extreme case, or brand new gas combined cycle plants as your fast response resource, you're adding to carbon emissions. Yeah. So this is kind of counter to the other stress of policy. So if we actually had carbon prices, just because you got to say it at least once if you're an economist in a webinar. If we actually had carbon prices, that would constrain the kind of fast response resources they could get and would push towards storage. But I'm just saying.
Right. Well, that's a good place to end. The hour is upon us. So those on the East Coast should get lunch. Those on the West Coast should get breakfast. Those in Europe should, I guess, have afternoon tea. And those in Asia should go to bed. So let me end by thanking both Dick and Paul for their thoughtful presentations. Let me thank all the questioners, very thoughtful questions. We couldn't get to them all, but please, be in touch with us. Again, the report's available online. I think there's further discussion there that may be helpful. And with that, I guess unless our technical support has any other comments, again, in a couple of weeks, we should be posting the presentation. And thank you all very much for participating.